Fourth methodology, sports-based learning. What is students in primary and even secondary school most like? Yes, of course, sports. Can we learn science thanks to sports? Yes, we can. Let's see. Probably, if you tell a student how to improve their meal menu to have better results in sport, or which is the menu and the food that Messi is following, is more attractive than study the carbohydrates, the proteins, and all of these things by themselves. Also, a game of football or basketball helps them to learn about the percentage, average, or probability which can find its use in physics problems. Let's see some examples that we can use in sports related with science. For example, right on time. Physics is used for precision timing of runners, for example, movements from starting blocks, which, thanks to pressure sensors, can detect better if an athlete has lifted the feet sooner than humans. Also, with the photo finisher, runner shoes, if they are lighter, much better. So there are very important physics in sport. Also, when we are using the force, each athlete must work in the technique that gives him or her the best chance of getting on the winner's podium. It's not exactly the same the force that Rafa Nadal needs in their arms than Messi, isn't it? The kind of work train that they would do is quite different. Also, another thing that nowadays is very popular is the material that you are using on it. For example, the swimmers. Nowadays, they are using a full body swimsuit with player-on panels. Thanks to this suit, they can eliminate skin friction, allowing water to flow over the body more easily. Also in cycling, hugging their bodies tightly to the bike's frame can reduce drag force by half. Another thing that sport and physics and science are really related is about the health and safety. Methods like ultrasound or daily use by physiotherapists to assist them in healing and monitoring sports people's injuries. The high frequency sound also helps to prevent some injuries before it happens. Also, in the Paralympics, they are using a leg up from wooden legs to the modern prostheses, carbon fiber ones. Also, there are really interesting approaches to learn problem solving in physics or stepwise method to study complex chemical reactions. Here, I show you some of the websites which are very interesting ones. This one is How Does Physics Help Sports, which shows you the different ones. Also, the physics of sports. Here you can find real-world physics problems and already solve it. And they are divided by different sports. So if you are really kind of kiting flying, skiing, snowboarding, and you have to solve these problems thanks to physics. Also, here you can find that how the chemistry and physics work in a different sports. And finally, I'm going to put all these websites links in Aula Virtual, but I want you to have a look at this video, which I think is very important.
Training log, day 14.
Last day, day 14 of the inactivity period.
It has been 2 weeks since we've done any exercise.
I've been quite tired.
And you'd think that conserving all this energy for 2 weeks, you'd have more energy, but that's not the case. Well, let's take a look back, 14 days.
So we're on our way to the clinical nutrition department here at the university to do a little chemistry experiment. We want to find out how our body's use of energy is related to the amount of exercise we do.
But first, let's explain the
I think that in these examples, it could use nowadays with the coronavirus as well.
basics of energy. Energy cannot be used up, just converted into different forms. The food we eat contains chemically stored energy in the form of energy-rich molecules, such as carbohydrates, proteins, and fats. When we do physical activity, these large molecules are first broken down to smaller molecules, such as glucose, that are transported to the muscles. Oxygen, which is also needed in this reaction, is transported from the lungs to the muscle, where it reacts with the glucose, producing carbon dioxide and water, and a small molecule called ATP, which is our body's energy currency. But we often hear the term calorie or kilocalorie when we talk about energy in food. A kilocalorie is actually a way to measure energy, and it's defined as the energy needed to increase the temperature of 1 kilogram of water by 1 degree Celsius. And to understand the meaning of this kilocalorie term in relation to how our bodies work, we are going to do a little chemistry experiment.
So the experiment you're going to perform right now is that during 2 weeks you're going to be as passive as possible with as little exercise as possible. And then during 2 weeks you will exercise as much as possible. And then we will see how big the difference is in energy expenditure.
So this is how we can do this. First, we drink a dose of so-called double-labeled water. It's normal water, except that both the hydrogen and oxygen atoms are isotopes of their normal form. An isotope has the same number of protons in the core, but differ in the number of neutrons. This water will then mix with the water we already have in our bodies and follow the water's normal pathways. All the marked hydrogen will go out with the urine together with some of the oxygen. The trick is that we will exhale some of the marked oxygen as carbon dioxide, and we will exhale more carbon dioxide if we train. Quite simply because we breathe more when we train, right? So depending on how much labeled oxygen and hydrogen we can detect in our urine, we can also calculate how much energy we have used.
So first, we wanted to investigate our energy expenditure during rest, which meant doing everything we could to do as little exercise as possible, but still live a normal life. No, seriously, this isn't training. And then, it was time to drink a new dose of double-labeled water and begin 2 weeks of hard training. And to help us do that, we have our very own personal trainer, Moa Nilsson at Fustra.
Okay, so we're done with 2 weeks of training. Now it's time to compare the results.
The chemical analysis of the double-labeled water from our urine samples showed that I went from using around 2,500 kilocalories per day during inactivity to around 3,800 kilocalories during weeks of training.
And I went from using about 3,000 kilocalories per day to about 4,700 kilocalories per day.
Well, if we start with the inactive period that you had, we can see that you had a very low energy need and you had very little physical activity. And that is shown to increase the risks of several diseases like heart diseases, cancer, overweight and obesity.
It may be obvious that the total inactivity option is not recommended, but what I found really interesting is that we can use chemical isotopes of hydrogen and oxygen and water to put a number on how many calories or chemical energy our bodies simply need to function and to do hard work. And it turned out that saving our energy by doing hardly any exercise at all actually made us even more tired. Why do you think that is?
A chemical experiment, like the one we just did, can give us valuable information concerning physical activity, different lifestyles, and our overall health. But chemical research related to sports is so much more than this. For example, a lot of biochemical research is done to understand how our bodies make use of different sources of energy, and how this may change during, for example, long-distance training. Studying and understanding oxygen uptake and transport help athletes train more efficiently. And chemists are also working to come up with improved materials in sports equipment. So get out there and burn some chemical energy. Just remember to eat right as well. Because chemistry is all around you and inside.